Good day. This is part 2 of the presentation. Is there a power of 6 that starts with a 9? We start with an outline of this part. First, we will recall of what it means for a power of 6, 6 to the n, to start with a 9. We will recall the definition of the transformation t that we introduced in part 1 and how that is used to characterize power of 6 starting with a 9. Then we will go a little bit further and explore when a power of 6 starts with any finite sequence of digits. And then we will prove Kroneker's theorem. In the first part, we saw how Kroneker's theorem answers that question. Does a power of 6 start with a 9? And the answer is yes, and we got an answer from Kroneker's theorem. Proof of Kroneker's theorem, and in fact, we will see that Kroneker's theorem gives us a little bit more. We will see that it actually gives us infinitely many n's, such that 6 to the n starts with a 9. So let's go to the recalling what we did in first part. We saw that 6 to the n starts with a 9 if and only if 6 to the n satisfies the inequality, that it's bigger than or equal than 6 times 10 to the k and less than 10 times 10 to the k for some k. Then we took logarithms, and then we defined a transformation, which is t of x equals x plus log 6. And we saw that that equation is equivalent to saying that t to the n, or 0, which is n log 6 mod, is in the interval log 9 log 10. So then the question was, is the orbit of 0 in the interval log 9 log 10? And more general, does it visit that interval? And last time we stated Kroneker's theorem, which in particular states that yes, the orbit of 0 visits that interval. In fact, visits every interval. Now, first we're going to see the question of what about the power of 6 starting not just with a 9, with say 92. And later we could ask the same question for your phone number. What does it mean to start with a 92? Well, starting with the 92, similarly, we can say it's going to be 6 to the n will be between 9.2 times 10, 10 to the k, in this case, or less than 9.3 times 10 to the k for some k. Here, instead of the 2, we should have a k in general. So then a power of 6 starts with a 9.2 if and only if the orbit of 0 visits the interval log 9.2, 9.3. Left closed, right open. Similarly, we can ask, does the power of 6 start with your telephone number? And you look at that interval, which will be smaller, but it will be log of the first digit of your phone number dot the rest, comma, the log that digit a little bit added at the end. That's 1. So there's a particular interval that you can construct for number so that the power of 6 will start at number if and only if the orbit of 0 visits that interval. And the n for which the visits, those will be n's for that power of 6 start number. Okay. So now let's look at the statement of Kroneker's theorem. Recall that. Let alpha be irrational. So now, instead of just looking at x plus log 6, we're going to look at this transformation that we introduced last time already, which is we call rotation by alpha, or translation by alpha in mod 1 in the unit interval. T of x equals x plus alpha mod 1. Okay. Kroneker's theorem says that when alpha is irrational, then for all intervals of positive length, I, there will be an n such that t to the n equals I. Now we're going to make an important remark, a consequence of this. It immediately follows from this property that there will be any such n. Well, find the first n, so you know that t to the n of x is in I. But we already said that Kroneker's theorem says every point has a dense orbit. So that point, t to the n of x, in turn will have a dense orbit. So there will be an m bigger than 0, so that t to the m of t to the n of x visits the interval I. Therefore, t to the m plus n of x will visit the interval. So now we have not only at n you visited, you also visited at n plus m, and you keep applying this, and you get that there will be infinitely many times, infinitely many integers, where you will visit the interval. Okay? The consequence of this is that not only is there one time, we saw 176 was the first time 6 started with a 9, but there will be infinitely many where it starts with a 9. And similarly, you have infinitely many where that starts, there you see with 9.2 and 9 or 9.2. Those are the times when the power of, where the orbit of 0 visits the interval log 9.2, comma log 9.3. So now we're going to look at the proof of Kroneker's theorem. We just saw the statement of Kroneker's theorem. We have seen an important consequence, how it answers our questions completely and gives us a bit more understanding what first digits about powers of 6s, powers of 2 also, because log of 2 is also irrational, and log of 3 is also. So now what we're going to do is prove Kroneker's theorem. Okay. The proof is based on two facts. First, we will prove two facts. The first one is that the orbit consists of distinct points. X, and look t to the n of x over all integers n, that consists of. As an aside, let me just say one remark here, that we are looking at positive orbits, and that's okay. You could look also at negative orbits. That would be because this transformation is invertible. But we're just looking at the orbit as you go forward. That was an aside remark, if you were wondering about what about the negative orbit. So the first part is that the orbit, the infinite orbit, is distinct. Orbit is distinct. All the points are distinct. That's the first part. The second part is that there are points in the orbit that are arbitrarily close to each other. That is, for any number epsilon, we think of epsilon as a small number, and any positive epsilon, there will exist some n and m. This that the distance between t and x and mx is less than epsilon. So there are those two facts that we will prove first. So let's prove the first fact, that all in the orbit are distinct. So let's assume not. Suppose that there is some m and n distinct, n and m, so that those points are the same. T and x equals tm x. Let's write down. So that means that x plus n alpha equals x plus m alpha. More. Canceling the x's, we see n alpha equals m alpha, 1. So that means that in the next line we should see n minus m alpha equals 0 mod 1. 0 mod 1 means it is integer. So that means that n minus m times alpha equals for some integer. So dividing by n minus m, we find that alpha has to be of the form k over n minus m, and that is a rational number. So alpha would have to be rational. But we have assumed irrational, that's a contradiction. Therefore, those points cannot be the same. So points in the orbit are distinct. And we have used in the fundamental way that alpha is rational. In our case, alpha log 6, and you're invited to show that log 6 is rational indeed. So now for the second part. The second part says that there are points in the orbit arbitrarily close to. Now we already know that it consists of distinct points, therefore it consists of infinitely many points. Give yourself an epsilon. We take epsilon. We think of epsilon as a very small number, positive small number. Choose an integer m such m is less than epsilon. So this is a basic, sometimes called the Archimedean property of the real numbers. Not sometimes, we call it the Archimedean real numbers. This is just as an aside for those of you who are studying real analysis, and you probably have learned how to prove that property. That for any positive number there's an integer, so that 1 over m is less than that positive real number. Now what we do is subdivide the unit interval into m equal subintervals. M equal subintervals. Pigeonhole principle, since the orbit is infinite, there must be at least one subinterval that has infinite points of the orbit. Therefore, there's a subinterval that has 2 points in the orbit, distinct points, So there are two distinct points which are at a distance less than epsilon, because they will have to be at a distance less than 1 over m, and 1 over m is less than epsilon. This concludes this part. Now, we haven't finished the proof yet. We have to finish the proof, and for the final part of the proof, we're going to use that t is a rotation. We're going to use a property of t as a rotation. We have to show more. We have to show that given any interval I, we don't know where it is, we can always find a point in the orbit that visits that interval. Okay? So you start with an arbitrary interval I of positive length. Suppose its length is positive length. Now we want to show that there's a point on the orbit that visits that interval. We know from the first part that we can find two distinct points in the orbit whose distance is small as you wish. Let's make that epsilon be length of the interval over 2. This just helps to visualize a little bit more y divided by 2. We could make an argument making that distance be less than the length of the interval. So there's a little bit of arbitrariness there just to make the picture a little bit easier to think about. So we can find 2 points whose distance is d, and d has been chosen to be less than the length of the interval, divided by 2 in this case. So let's look at those 2 points, and we'll assume one is bigger than the other. So now if we apply t to the m minus n to tn, we get tm. Okay. So now we're going to look at this picture just to think about. Suppose that we're rotating by alpha, think about this, and suppose that those 2 points happen to be, for this particular case, alpha and 4 alpha, and they happen to be at a distance d. You see alpha. Now, what is m minus n? In this case, m minus n will be 3, because one is t to the 1 and the other one is t to the 4th. You subtract this t. So what we're saying is that if you apply t to the 3rd to alpha, you get the other point, you get 4 alpha. But now the important thing, it follows that because t to the m minus m is also a rotation, that is t to the 3rd power is also a rotation, when you apply t to the 3rd to 4 alpha, you must get another point that is exactly at distance d from 4 alpha. The other point has to be at the same distance from 4 alpha as 4 alpha is from alpha. So here we see in the picture, alpha, you apply to the 3rd, you go to 4 alpha, and then you apply t to the 3rd to 4 alpha, you get to 7 alpha. And then you apply to the 3rd to 7 alpha, you get to 11 alpha, but 11 alpha must also be at distance d. As you continue, then you end up with points in the unit interval which will be at distance d from each other, and then at the end they may be a little bit less than d. So you will have obtained a sequence of points in the interval of distance d from each other, and since the interval has length 2d, it must be the case that at least one of those points is inside that interval. You cannot have all those points miss the interval, okay, since they are distance d from each other and the length of the interval is bigger than 2d. So this part concludes the proof. So we're using the fact that t to the m minus n is a rotation. We apply that and we just rotate by that around, and we subdivide the interval into points that are distance d apart. This concludes our proof of Kroneker's theorem. Thank you for the second part.